You know how sometimes the lecturer asks you to show that a parameterized problem is FPT. And then you think about it, some more, and then you come to the conclusion that it's impossible to show that this problem is FPT. Well, in this lecture, we are going to see the tools that we can use to show that the problem is not FPT unless some complexity classes collapse. We're going to see the theory behind parameterized complexity, and we will see some case studies where we show that some parameterized problems are not FPT subject to these assumptions. As usual, n is our instance size, k is the parameter, p is the class of problems that can be solved in polynomial time, fpt is the class of parameterized problems that can be solved in time f of k times a polynomial in n. Xp is the class of those parameterized problems that can be solved in time f of k times n to the power g of k for some function g. So those are those problems that can be solved in polynomial time when k is a constant. But in between fpt and xp, we have these parameterized intractability classes. So even for problems that are in xp, they allow us to show that they are probably not in FPT unless something unexpected happens. So, and here, as soon as we can show that the problem is W1 hard, this then means that it's not FPT unless these complexity classes are the same. And we are going to see how to show W1 hardness. Okay, let's start with two problems that we know: vertex cover and independent set. So in vertex cover, of course, the input is graph G, an integer k, the parameter is k, and the question is whether G has a vertex cover of size k, and for independent set, we ask whether G has an independent set of size k. So we know that these problems are both NP-complete if we disregard the parameter, so the non-parameterized versions of the two problems are NP-complete. So there exists a polynomial time reduction from vertex cover to independent set, and also from independent set to vertex cover. We also know that vertex cover is FPT. So we know that this problem can be solved in FPT time. We don't know whether independent set is FPT. So actually we haven't seen an FPT algorithm for independent set, and actually nobody has come up with an FPT algorithm for independent set. So could we somehow show that, well, independent set is maybe W1 hard? What tool do we have to show hardness? So we have seen polynomial time reductions. But we know that there's a reduction in both ways. So we know in particular that there's a polynomial time reduction from independent set to vertex cover. But we don't know whether independent set is FPT. So in polynomial time, we know that we can take an instance for independent set, transform it into an instance for vertex cover, we can solve vertex cover, and this will then give us a solution for independent set. So, but what's the issue here? Why don't we think that independent set is FPT based on this reduction? Well, the problem is that, so the issue is that the parameter changes. So when we transform an instance from independent set to vertex cover, so we know that the graph has an independent set of size k. So G, k is a yes instance for independent set. If and only if the graph has a vertex cover of size n minus k. So n is the number of vertices of my graph. So G comma K is a yes instance for independent set if and only if G comma N minus K is a yes instance for vertex cover. But, well, actually, since the parameter has changed, an algorithm, an FPT algorithm for vertex cover, wouldn't help us in getting an FPT algorithm for independent set. Because, well, when we do the transformation, the parameter for vertex cover becomes N minus K. So this algorithm for vertex cover would be exponential in N minus K. But that's not allowed for FPT algorithms. So the reason why we cannot just use polynomial time reductions is because they may change the parameter. And so we will want a different kind of reductions. So we will want the reduction to produce an instance where the parameter of the resulting instance is bounded by a function of the parameter of the original instance. So if we could find a reduction from the first problem to the second problem where the parameter now becomes maybe k squared, and then we use an algorithm that is exponential in k squared, that's still okay, right? So as long as the parameter is just a function of the original parameter, we are fine. But as soon as we have some other ingredient in the parameter that cannot be upper bounded by k, such as the number of vertices here, then we are in trouble. Another advantage that we can use is that, well, the reduction is allowed now to take FPT time instead of just polynomial time. Because, well, we don't need the transformation to take polynomial time because, well, in total we have FPT time at our disposal, so we can use it if we want. Very often polynomial time reductions will be enough to show things such as W1 hardness. Okay, so this brings us immediately to the concept of a parameterized reduction. So a parameterized reduction from a decision problem pi1 to a parameterized decision problem pi2. So that's no, it's not a polynomial time algorithm. So it's an FPT algorithm. So in FPT time, we should be able to compute it. So we should be able to compute an instance for pi2. Let's call it I prime comma k prime. That is equivalent. So on the left-hand side we have yes instance if and only if. On the right-hand side we have yes instance. So the parameter shouldn't increase too much. So we have that, so k prime should be upper bounded by some function of k. And we also have that, well, the transformation takes FPT time. We have that one already. Okay. So now we say that there exists a parameterized reduction from the parameterized problem pi1 to pi2 if such an algorithm exists, and we write that pi1 is smaller or equal, and then we have a FPT subscript here, pi2. So we can assume, as usual, that f and g are non-decreasing. So we can use these parameterized reductions now to obtain new FPT algorithms. So very similar as in the theory of NP completeness, we can now use our reduction to solve new problems. So if pi1 and pi2 are parameterized decision problems, and pi1 can be reduced to pi2 by a parameterized reduction, then if we have an FPT algorithm for pi2, then we can obtain an FPT algorithm for pi1. So and this works just by taking an instance for pi1, applying the reduction. So in FPT time, we create an equivalent instance for the pi2 problem. And now we use an FPT algorithm for pi2 to solve that instance, and we are guaranteed that the parameter is not too large. And then we just return the result. So in order to go or to see the other side of the coin, where we use reductions in a negative way, where we show negative results via reductions, let us introduce Boolean circuits and then some problems on Boolean circuits. So Boolean circuit is a directed acyclic graph, and the nodes are labeled as input nodes. So every node within degree 0 is an input node. Every node within degree 1 is a negation node. Every node within degree at least 2 is either an AND node or an OR node. So our Boolean circuit will have some inputs. So on the inputs we are going to place Boolean values. And then these propagate through the nodes of the circuit. So at the negation node they get negated, at an AND node the result is 1 if and only if the inputs were all 1, and at an OR node we have that the result is 1 if and only if at least one of the inputs was 1. So, and then at the end there's a single output node that has out degree 0. So, and that's where the result of the computation is stored. So we have many input nodes and one single output node. So now the depth of the circuit is the maximum length of a directed path from an input node to the output node. Okay, so far everything is quite common. And now the special thing about these circuits is that the weft of a circuit is the maximum number of nodes that have in degree at least 3 on a directed path from an input node to the output node. So if we look at all the paths from an input node to the output node, and we count the number of nodes with in degree at least 3, and take the maximum over all of those, that gives us the weft of the circuit. Okay, let's see an example. So here we have 5 input nodes on the bottom. We have one output node on top. We have a range of negation nodes, and then we have some disjunctive nodes that compute an OR. The output node computes an AND. So this circuit has depth 3. Actually, all the paths from an input node to the output node have length 3. So we count the number of edges. 1, 2, 3. The weft is 1 because, well, the only node that has in degree at least 3 is the output node. So we count only those nodes with in degree at least 3, and that's only the output node. So on each path from an input node to the output node, there's 1 degree at least 3 vertex. Our main problem about circuits is the weighted circuit satisfiability problem. So the input is a Boolean circuit C and an integer k. The parameter is k, and the question is whether there is an assignment with weight k that satisfies C. So an assignment is an assignment of Boolean values to the input gates, and then once we have an assignment, we can propagate these values and we get some value at the output node. Now, if we get a 1 at the output node, we say that this assignment satisfies the circuit. And now the weight of this assignment is the number of input nodes that we set to 1. So the number of 1s in the input is our weight. The question is there an assignment with weight k that satisfies C? So is it possible to set exactly k input nodes to 1 and all the others to 0, such that when we propagate these values through the circuit, the output node gets set to 1. Okay, there's an exercise that asks us to show that weighted circuit satisfiability is in XP. So is there an algorithm which for any constant value of the parameter works in polynomial time? Okay, so this problem will be in XP. Now we're going to look at special cases of this problem. So namely, we're going to restrict the input circuit to some class of circuits. And so which classes are we looking at? Well, we are going to restrict the depth of the circuits and the weft of the circuits. So the class of circuits, calligraphic C sub t, d, is the circuits with weft at most t and depth at most d. Now we can define the weighted circuit satisfiability problem for any class of circuits. So instead of having an arbitrary Boolean circuit as an input, we have a Boolean circuit from this class in our input, and the rest of the problem is the same. So the only thing we did here is to restrict which Boolean circuits we can have in our input here. We are now ready to define the W classes. So let t be an integer, that's at least 1. A parameterized problem pi is in the parameterized complexity class Wt if there exists a parameterized reduction from pi to the weighted circuit satisfiability problem for circuits with weft t and depth d for some constant d that's at least 1. So the crucial part here is that so the weft needs to be bounded by t. So we need to be able to encode our problem into a weighted circuit satisfiability problem where the weft is bounded by t and the depth is also bounded but by some arbitrary constant. So the only thing that we are not allowed to do is to have an unbounded depth. Okay, so I claim now that independent set is in W1 and that dominating set is in W2. Let's see what dominating set means. So a dominating set of a graph G is a set of vertices such that, well, every vertex of the graph is either in this set or it's a neighbor of a vertex in this set. And for the dominating set problem, the input is a graph G and an integer k. K is our parameter, and the question is whether G has a dominating set of size at most k. So I'm not going to prove this rigorously, but I'll give you a picture. So on the left-hand side, we have a graph. And so let's say that this is our input graph for independent set or for dominating set. And then here I show you how to transform this graph into a circuit. So the middle one is the circuit for independent set, and on the right-hand side we have the circuit for dominating set. And as input, they have nodes that correspond to the vertices of the graph. And the commonality is that if we set an input node to 1, this means that we add the corresponding vertex in the graph to the independent set or the dominating set. Okay, so let's think about independent set first. So what are the constraints? So if we set some input node to 1 here, so what that means in the graph is that we add this vertex to our independent set. So in the graph, this means that we are now not allowed to select B or C into our graph. So that means that, well, the circuit should prevent us from setting B to 1 or from setting C to 1. What does the circuit? So suppose, for example, we would set B to 1. then what happens in the circuit? Well, at the next stage, they both get negated. And here we have an OR. And so we have 0 or 0, that gives 0. And then in the output, since this is a big AND, we will have a 0 in the output as well. So as soon as we set A to 1 and B to 1, we get an output that's 0. Because, well, in the graph it's not allowed to select both A and B into the independent set. And the circuit nicely constrains that, well, on this level here before the output node, we have a node for each edge. And so this node checks that we didn't select both endpoints of the edge into our independent set. So it prevents us from setting both A and B to 1. But if we actually select some other set of vertices like A and D, set those to 1 and everything else to 0, then, so what happens? So on the next level we get a 1 here, 1, 0, 1, and then we can observe that all of these ORs here are 1, and now the output is also a 1. So the only constraints that we need to encode is that for each edge of the graph, we cannot select both endpoints. And then an independent set of size k in the graph corresponds to an assignment of weight k in this circuit. What about dominating set? So for dominating set, what do we need to ensure? So we need to ensure that each vertex is dominated by a vertex that we selected. So here now we will have a constraint on the level before the output. We'll have a constraint for each vertex of the graph that says that, well, either this vertex is 1 or one of its neighbors is 1. And this can be just done by an OR. So let's see. So I think this node would correspond to the constraint on E. And it says that, well, either E is 1, or D is 1, or C is 1. So at least one of these three vertices must be set to 1, so as to dominate the vertex E. And we have such a node in the circuit for each vertex in the graph, and that ensures that then that every vertex will be dominated because, well, we have a big AND at the output node. Okay, so now if we look at the rest of these circuits, we observe that the first circuit has in degree at least 3 only at the output node. And for the second circuit, it has in degree at least 3 at the output node and also at each node on the level before the output node. So on a path from the input node to the output node, we will encounter 2 vertices or 2 nodes with in degree at least 3. So the first graph has weft 1, and the second Boolean circuit has weft 2. And the depth of these 2 circuits is also upper bounded, so by 3 for the first one and 2 for the second one. And so this picture now gives us an idea how to show parameterized reductions from independent set to WCS on C13, so Boolean circuits with weft 1 and depth 3, and from dominating set to Boolean circuits with weft 2 and depth 2. And so now, of course, a parameterized decision problem is now WT hard if for every parameterized decision problem pi prime in WT, there is a parameterized reduction from pi prime to pi. So this models exactly what we had for NP hardness. And now pi is WT complete if pi is in WT and it's also WT hard. So again, for the completeness for WT, we need membership and hardness. In this lecture, we're mostly going to focus on hardness. Membership is actually a bit more difficult than for NP, so it's not always easy to get membership in a WT class. Well, we saw two sketches of membership proofs here, but it's not always very easy to design these Boolean circuits. Okay, and now we have that Downey and Fellows showed that independent set is W1 complete and dominating set is W2 complete. So we saw a picture that reduces like these problems to circuits. If you also reduce the other way around, if you reduce the circuits to the graph problems, then you get completeness for W1 and for W2. So independent set is W1 complete and dominating set is W2 complete. So to show now that the parameterized problem is WT hard, we select a known WT hard problem and give a parameterized reduction to our problem that we want to show is hard. So as I mentioned, we will not care too much about WT membership. We mostly focus on using the reductions to show hardness. And so this FPT, this parameterized reduction, works of course by designing an algorithm that for any instance for pi prime produces an equivalent instance of pi, and then the parameter of the resulting problem must be upper bounded by a function of k prime. And we also need to show that, well, this reduction can be done in FPT time. And I mentioned already that usually we are able to come up with polynomial time reductions that do this. So for the examples here, well, it was quite easy to reduce the graph problems to circuit problems in polynomial time. And the parameter k stayed the same because, well, every selection of a vertex from our graph corresponded to setting exactly one input node to 1, and that was the weight of this assignment. So we have already seen that independent set is W1 complete and that dominating set is W2 complete. Let's look at another example. So we want to show that Clique is W1 hard. So and the Clique in the graph is of course a subset of vertices that are all pairwise adjacent. And the question is whether G has a clique of size k for an input graph G and an integer k, and k is our parameter. So to show W1 hardness, remember that we need to choose a problem that we know is W1 hard and reduce it to our problem. So we will reduce from independent set. So we want to show that so independent set reduces via a parameterized reduction, so we have one of these FPT reductions, to Clique. Okay, how do we do this? Well, we already saw a very tight relationship between independent sets and cliques. But we also saw a tight relationship between independent sets and vertex covers. And for independent sets and vertex covers, we saw that, well, the reduction doesn't really work out because we changed the parameter too much. So what happens for Clique? So let's see. If we have an independent set in a graph G, so let's say this is an independent set of size k, let's say exactly k, inside our graph G. Okay, So let's compute this complement graph. So in the graph G prime, now, so what was an independent set in G? Well, in G prime, we transform every non-edge into an edge, and every edge into a non-edge. So here, we didn't have any edge between these vertices in the independent set. So that means if we look at the same vertices in the complement graph, well, we have all possible edges between them. Okay, so that's nice because now actually in G bar we do find a clique of size k. So there's no issue with the parameter here because an independent set of size k in G corresponds to a clique of size k in G bar. Okay, so our reduction can now take any instance for independent set and produce an equivalent instance for clique. And so we do this just by setting the parameter to be the same and by taking the graph and switching the edges. So whenever we had an edge, we have no edge. If we had no edge, now we have an edge. So for every pair of vertices, for every pair of distinct vertices, we have an edge now if we had no edge in G. So we just need to show that G, K is yes instance for independent set if and only if G prime, K prime is yes instance for clique. So we have two directions to prove. So if S is an independent set of size K in G, then, well, for every two vertices in S, we had no edge in G, therefore we do have an edge in G bar. So we conclude that so this set of vertices that was an independent set in G is a clique in G bar. And also it has size K because we didn't add or remove any vertex. Now for the reverse direction, if we do have a clique of size K in G bar, then clearly this also corresponds to an independent set in G just because of how we constructed G bar from G. The parameter hasn't increased, so K prime is actually equal to K. And the construction can clearly be done in FPT time, even in polynomial time. So I just wanted to go through the various steps that we need to prove. So we need to prove this, we need to give a construction, we need to show that, well, it creates an equivalent instance, that the resulting parameter is bounded by a function of the original parameter, and also that the reduction can be done in FPT time, and oftentimes in polynomial time. So we conclude that clique is W1 hard, and so in the exercises we will see more W1 hardness proofs. There's some further reading about the parameterized complexity part, about the real complexity theory and these W classes, and here are the references. The dash here means that, well, those are the same authors as in the previous reference.